after we get the idea of conservation of mechanical energy and conservation of energy, that is mechanical energy, and the conservation of linear momentum of a system of particle, let us apply these two conservation principles for a system of particles through some conceptual problems. The first problem I am taking, the problem of two blocks interconnected by a spring. The block number 1 is pressed against the wall. When you apply a force on the block 2 in horizontal direction, you press it, the spring is pressed. In consequence, this block 1 remains in contact with the vertical wall. X naught let be compression of the spring initial. If we release the system, what is the system? The system of two blocks with this spring. The spring is massless or light spring. No friction anywhere. Friction is a conservative force. When there is no friction, of course we can conserve the mechanical energy. Since friction is absent, we have the chance of energy conservation. We have the chance. The principle of conservation of energy says that whenever the work done by the non-conservative force is equal to 0, the mechanical energy of the system remains conserved. Work done by the non-conservative force will be 0 only when either non-conservative forces as a whole will be equal to 0 acting on the system, or even though the non-conservative forces will act, they must not do any work. If you draw the ABD, somebody is pushing the block 1, that somebody is none other than the vertical wall. This vertical wall pushes the block number 1 with some force, let it be N. Therefore, if you take this as the system of two particles, the system experiences a net force from outside. Therefore, we cannot conserve the linear momentum of the system. Since the system experiences net external force from outside, a net force from outside, or we can say net external force, that is equal to N. The net impulse is equal to integral n dt. And this net impulse is not equal to 0. According to impulse momentum equation, net impulse is equal to change in linear momentum of the system. Since the net impulse, that is integral n dt, is not equal to 0, we can say that the change in momentum will not equal to 0. Therefore, momentum of the system does not remain constant so long as the block remains in contact with the vertical wall. So long as the block, which block? Block 1 remains in contact with the vertical wall. This means that so long as n is not equal to 0, so long as the vertical wall is pushing the block 1, the momentum of the system will keep on increasing. Momentum increases its magnitude. As a result, the block 2 will start moving towards right because the spring force will push the block towards right. The spring force will push the block 1 towards left, but the block 1 cannot move because it is constrained by the vertical wall. Vertical wall is a rigid wall. It can give any amount of force to nullify the spring force. For all the times, so long as this is in contact with the vertical wall, the normal contact force given by the vertical wall in horizontal direction on the block 1 will nullify the spring force. So that always this block 1 will not accelerate at all, whereas the block 2 will have some acceleration that is equal to the spring force upon its mass. In this system, these two blocks, block 1 does not accelerate, block 2 accelerates. However, the center of mass has an acceleration because the net force acting on the system is equal to n upon the total mass of the system is m1 plus m2. The center of mass will accelerate. The center of mass will accelerate. When the center of mass accelerates, the velocity of the center of mass changes. Or you can say that the momentum of the system will change, will keep on changing. The momentum of the system will keep on changing. Our job is to analyze the system, whether the system can conserve its linear momentum or not, whether the system can conserve its mechanical energy or not. This is a matter of analysis. One thing is very clear, that since the net force acting on the system is not equal to 0, the net impulse is not equal to 0. According to impulse momentum equation, net impulse is equal to change in momentum of the system. Since the net impulse is not 0, the change in momentum is not equal to 0. Therefore, the system will change its momentum until the block 1 remains in contact with the vertical wall. Up to that moment, the work done by the tension in the spring, so-called the spring force, the work done by the tension or the spring force on the block 1 will be 0. The work done by the normal contact force on the block 1 also will be 0, because these two forces act on the block 1 and the block 1 is constrained not to move. Therefore, the displacement of the block 1 is 0. Since the displacement of the block 1 is 0, the work done by all non-conservative force, or you can call it normal reaction, and the spring force and normal reaction offered by the ground and the gravitational force, work done by all these forces on the block 1 will be equal to 0. When this force does not perform any work, this force doesn't perform any work, this force will do no work, then we can say that on the entire system, the non-conservative forces, the normal reactions will perform no work. The constant forces will not perform any work here. Therefore, the total mechanical energy of the system will remain conserved, or you can say change in total energy, mechanical energy of the system will be equal to 0, or the mechanical energy of the system will remain conserved. So here we can conclude that this system can conserve its mechanical energy, but momentum of the system is not conserved so long as this block is in contact with the vertical wall. Now we have to wait until the block will lose contact with the vertical wall. The block will lose contact because normal reaction will vanish. This is because net force acting on the block is 1 will be equal to 0. The net force is N minus spring force. Spring force varies, N also will vary, such that net force acting on the block 1 will be equal to 0. Why does the spring force vary? This is because the block 2 will move towards the right. In consequence, the spring will get stretched. The elongated spring, the spring will get stretched. It's not okay to say stretched. Already the spring is compressed. It's not stretching. The compression is decreasing. The compression decreases from x0 to 0. The compression decreases from x0 to 0. So it is not the matter of stretching of the spring. The spring is originally compressed. The compression gradually decreases to 0. In consequence, the spring force, which is equal to the stiffness of the spring into the compression or elongation. In this case, that's not elongation. Both elongation and compression can be called deformation, and in this formula, that formula is called Hooke's law. X is called deformation. Here the deformation is compression. When the block 2 moves towards right, the x decreases. When x decreases, the spring force decreases. On the block 1, the spring force minus normal reaction will be equal to 0 because its acceleration is 0. When the spring force is exactly equal to normal reaction and the spring force decreases to 0, the normal reaction also will decrease to 0. When the normal reaction will vanish, the block 1 will lose contact, and thereafter the net force acting on the system will be exactly equal to 0. Hence, the momentum of the system does not change, or momentum of the system we can say remains conserved. After the block 1 loses contact with the vertical wall. However, the mechanical energy always remains conserved due to the absence of friction. Here, mechanical energy is conserved in both the cases, but the momentum is conserved in the second case. So long as the block is in contact with the vertical wall, the momentum cannot be conserved. The moment the block 1 loses contact with the vertical wall, you can conserve the linear momentum of the system because no net force is acting on the system thereafter. So this is a beautiful problem, and theoretically we analyzed the possibility of conservation of linear momentum and energy, and I will expedite this problem, and I will tell you to calculate different parameters of this set. If we release the system, describe or analyze the motion of the system. Analyze the motion of the system. The system has 2 blocks. How do the blocks move? How do the blocks move? How does the center of mass move? By using the principle of conservation of linear momentum, conservation of energy. After the block 1 loses contact with the vertical wall, we can accidentally solve the problem. Let me recast the problem as another set of problem, another example to find several parameters. The same system is released from rest. This is the initial compression of the spring. When the block 2 moves towards right, at this position, the spring will get relaxed because the elongation of the compression of the spring, not elongation, compression of the spring will be 0. So the spring is said to be relaxed. At the same time, block 1 will experience no normal reaction from the vertical wall. Even though we cannot conserve the linear momentum of the system from this position to this position, still we can conserve the total mechanical energy of the system between these two positions. Conserving the mechanical energy we can get del U plus del K is equal to 0. The spring potential energy changes from half K x naught square to 0 because here the spring is relaxed. Final minus initial potential energy. This final, this is initial. Change in physics is always final minus initial. Plus. Here velocity is 0. Here velocity is 0. Here velocity is 0 because it does not lose contact. Here velocity, let it be v. Or you can call v naught. The kinetic energy changes from 0 to half m2 v naught square. Its mass is m2, its mass is m1 say. Initial kinetic energy is 0. This gives us the velocity with which the block 2 will move when block 1 is about to lose contact with the vertical wall. This velocity is equal to k by m2 square root of this into x naught. Find v naught. Next we can find velocity of center of mass when the block 2 has this velocity v naught or block 1 is about to lose contact with the vertical wall. Velocity of center of mass is equal to m1 v1 plus m2 v2 by m1 plus m2. Its velocity is 1, its velocity is 0, its velocity is v1, that's equal to 0. This velocity is v2 is equal to v naught, m2 v naught by m1 plus m2. Just substitute the value of v naught. Which is equal to k by m2 square root into x naught. This gives us m2 by m1 plus m2 into square root of kx naught. Next we can calculate, find the maximum normal reaction n. N is maximum only when x is maximum, because n minus spring force is equal to mass of the block 1 into acceleration of the block 1, that is equal to 0. So n is equal to Fs. Fs is equal to k into x. N is maximum only when x is maximum. So maximum value of n is equal to k times the maximum value of x, that is x naught. Initially, the vertical wall can give maximum pushing force. Next you can find the impulse offered to the block M2. Now this is a system. If you take M2 as a system, the impulse on the block 2 is equal to change in momentum of the block 2. Impulse momentum equation applied on the block 2 only. The block 2 changes its momentum from 0 to m into v naught. Therefore, final momentum minus initial momentum is the change in momentum. It changes its momentum in positive x direction because the spring is continuously pushing it towards positive x direction or towards the right. In other words, we can say that the impulse acting on the block 2 is directed towards the right. And we know the velocity of the block 2 at this instant. We have to use the mass of the block 2, that is m2. And v naught already we have calculated as the square root of k by m2 into x naught. So you can just write k into m2 square root of this into x naught. This is the answer. Let us take this system of two particles m1 plus m2. They are connected by the spring. If you push m1 or project m1 with the velocity v naught, what will happen? Analyze the system. Analyze the system. We can calculate many more factors, many more parameters, such as position of m1, velocity of m1, acceleration of m1 with respect to time, position of m2, velocity of m2, its acceleration as a function of time, the elongation of the spring force as a function of time, the position, the velocity, the acceleration of the center of mass as a function of time. So many things you can calculate. But here, let us calculate few interesting things, such as the center of mass velocity. Find the center of mass velocity. Find the center of mass velocity, a velocity of the center of mass. Center of mass velocity can be given by the simple formula of the system. Center of mass velocity can be given as m1 v1 plus m2 v2 by m1 plus m2. At this instant, velocity of m2 is 0, velocity of m1 is v naught I cap. By m1 plus m2. This gives us velocity of the center of mass as m1 v naught I cap by m1 plus m2 answer. The next question, the total momentum or momentum of the system. find the momentum of the system is equal to sum of moment of all particles of the system, that is m1 v1 plus m2 v2. If you divide both, divide and multiply, the denominator and numerator by the factor m1 plus m2. This factor remains unchanged. m1 v1 factor plus m2 v2 factor upon the total mass of the system is none other than the velocity of center of mass into this is the total mass of the system. So, the momentum of the system can be given as total mass of the system into the center mass velocity. Let the total mass be capital M into center mass velocity is Vc. Find the momentum of the system if center mass has velocity Vc. If center mass velocity is given, directly multiply the center mass velocity with the total mass of the system. That will give us momentum of the system. But in this question, center mass velocity is not given, velocity of this particle is given. So we can just write momentum of the system is equal to this mass velocity is 0, this mass velocity is v naught I cap. Therefore, we can just write m1 v1 naught I cap. Answer. These are some basic questions you can pose before we ask some more typical questions. Let us calculate the maximum elongation of the spring. The spring will elongate. This is because initially this block 1 M1 moves towards the right with respect to the block M2. Velocity of the block 1 with respect to 2 is equal to v naught I cap at time t equal to 0. When the relative velocity of 1 with respect to 2 is towards the right, the rate of change of the position vector of 1 with respect to 2, that is none other than the length of the spring will change at a rate which is equal to v naught, where R12 is equal to L naught I cap initially. This gives us the idea that the length of the spring will change at a rate of V naught initially. But after some time, this block M2 will be pulled by the elongated spring. Once the spring gets elongated, the elongated spring will pull the block M2 towards right, and it will pull the block M1 towards left. Whereas M1 is moving towards right with certain velocity which will be obviously less than V naught, because V naught is its initial velocity. Initially the spring was relaxed, no deformation, no elongation, no compression. Therefore initially the spring force will be equal to 0. But due to the relative velocity between these two blocks, the spring will get elongated. Once the spring elongates, the spring will start pulling these two blocks, one towards left, the other towards right. As a result, the block M1 will slow down because it moves towards right, whereas the force acting on the block 1 is towards the left. So the force decelerates or retards the block M1. Kx retards the block M1. In consequence, velocity of the block 1, that is V1, decreases. Now come to the second block. On the second block, the spring continues to pull towards right. Initially, the second block was at rest. Therefore, the force Kx acting on the block M2 will increase its speed, or you can say that M2 will speed up. M2 will speed up and M1 will slow down. Velocity of the block 2, that is V2, will increase. And the velocity of the block 1 will decrease. V1 will decrease, V2 will increase. We can understand this by analyzing each block physically, by drawing the free body diagram on each block along horizontal direction. When this block will speed up, this block will slow down, time will come. Both the blocks will move with some velocity at any instant. At any instant, both the blocks will have same velocity. V1 decreases, V2 increases, time will come, both the velocities will be exactly equal. Or you can say that the relative velocity between these two blocks will be 0 at that instant. Since relative velocity is equal to rate of change of length of the spring when the magnitude of relative velocity will be 0, the length of the spring will be a maximum quantity. When the relative speed between these two, or relative velocity between these two blocks will be 0, the string will be stretched to its maximum extent, or the length of the spring will be maximum at that instant. We have to calculate the maximum elongation of the spring. When the spring will be having maximum elongation, the instant when both the blocks will move with some velocity. Block 2 will accelerate or will speed up, and block 1 will slow down. Both the things are happening at a time. Time will come when both the blocks will move with some velocity. At that instant, the spring will have maximum elongation. This is the physical analysis. After that, we will be able to solve the problem by using the concept of conservation of mechanical energy and conservation of what? Linear momentum.